Hi, in this video, I will be showing you problem number 51 of chapter 15, section 2. Evaluate the integral by reversing the order of integration. Integral 0 through 1 and integral 3y through 3 e to the x square dx dy. So the key word here is reversing the order of integration. That is the technique we have to use. In fact, this problem cannot be done by keeping the problem the way it is. So if you look at the inside integral, it is e to the x square dx, which cannot be integrated by the regular integration techniques. So we are going to use the reversing the order of integration technique without changing the region over which it is integrated. Still, the region should remain intact, which means the domain over which the surface is defined. When we say we are evaluating a double integral, what we are finding is the area is a volume of the solid under the surface over the region. Okay, so double integral means evaluating the volume. So the region should not change, but the limits of the variable can be changed accordingly, suitably. So we cannot integrate if we don't reverse the order of integration and suitably change the limits of the variable. So let's first sketch the diagram or explain the region given in the problem. So x runs from 0 to 1, y runs from 3y to 3. The region of integration given in the problem is R. It's set of all x, y such that 0 less than or equal to 0 less than or equal to y less than or equal to, so y, the outer variable is y, that corresponds to these limits 0 through 1. And the inner one is x, the limits are 3y to 3. So x runs from 3y to 3. So that's what the problem is given. The graph of the region will tell us how to manipulate the variables here. So graph the region. So x and y axis here. So x runs from, so we need up to 3 for the x. So x is plotted, 3 units is shown on the x-axis. And then we are also given this graph x equal to 3y or 3y equal to x, which is this graph here. Then they meet at the point. So the region is shaded here. And then this point is going to be 3, 1. So if you plug in x equal to, if you plug in y equal to 1, x becomes 3. So this is the region given in the problem. The region should not be changed for our revised order of integration, but the limits of the variable can be changed. The limits of the variables need to be adjusted, keeping the region over which the surface is defined fixed. So the revised limits for the variable, the revised limits for x and y will be as follows. So we can write this as all those x, y. Instead of making the y fixed limits, we will keep x fixed limits. So that means if you look at the figure, x runs from 0 through 3. So we can write 0 less than or equal to x less than or equal to 3. And y can vary from this point to this point, which is from this to this. That will be y equal to 0 to y equal to 1/3 of x. X equal to 3y. 3y can be solved for y, which is 1/3 of x. So these are the new limits for us. So if we use these new limits, we can actually integrate the given integral easily. So the double integral 0 through 1 for y, integral 3y to 3 for x, e to the x squared dx dy. When we change the limits, x runs from 0 to 3, y runs from 0 to 1/3 of x, e to the x squared dx dy. dy dx, because we are reversing the order of integration. So the dx dy changes to dy dx, and then the limits are suitably changed. Always remember the fixed limit should be outer integral, outer variable. The varying limit should be the inner integral. That is integral 0 through 3 y times e to the x square 0 to x by 3 dx. Because when we integrate with respect to y, x is constant, so constant times y is this integral. We have to plug in the limit 0 and x by 3, evaluate the inner integral, then again integrate with respect to x. So it is integral 0 through 3 x over 3 e to the x square, and the lower limit is 0. 1/3 can be pulled out. 1/3 integral 0 through 3 x e to the x square dx, and this can be easily done by u sub method. So let u be equal to x square, so du is 2x dx, and then also we change the limits from x to u. When x equal to 0, u will be equal to 0 as well. When x equal to 3, u equal to 9, because u is equal to x square. Now, plugging in the values for u now, 1/3 integral 0 through 9, then e to the u x dx. X dx can be solved, which is equal to du over 2. du over 2. So 1/3 integral 0 through 9 e to the u, and then du over 2. That 2 can be brought outside the integral, so it's 1/6 integral e to the u du between the limit 0 and 9. So it is 1/6 e to the 9 minus e to the 0. E to the 0 is 1, so it is 1/6 of e to the 9 minus 1. So double integral e to the x square dx dy with the given limits becomes 1/6 e to the 9 minus 1. So if you look at this new figure I have drawn here, that will explain better how we come up with these new limits. We have not changed the region, but we are only changing the limit. So now we are doing x running from 0 to 3, then y runs from here to here. So it's going to be y equal to 0 through y equal to 1/3 of x. So reversing the order of integration is very powerful for some problems where if you keep the integration as is, it may not be possible for us to integrate. By applying the reversing the order of integration process, we can easily integrate the given problem. Hope this video helps.